Hello and welcome to Math with Beth, and we are going to talk about symmetry with some of the graphs we've been looking at. And there are a couple different types of symmetry. So first, if we say that something is symmetric or has symmetry over the y-axis, since this is the y, one way of thinking of it is, does that cut the graph right in half? Another way of thinking of it is, does that kind of act like a mirror where this part is the same as that part? It's kind of like a mirror image. So this is an example of something that has symmetry over the y-axis. Something that has symmetry over the x-axis would be the same, except it'd be this line that would be cutting it in half. If it has symmetry over the x and the y-axis, it just means that this one works, which it does. And this line also works as far as cutting it in half. And then finally, the trickiest one to kind of see from the graph is being symmetric over the origin. It means it's being flipped kind of over the line here. But another way of thinking of it is if you take part of the graph and flip it over the y, and then flip it again over the x, would you get to the other part of the graph? That's kind of how I think of it visually. If I were to flip this and flip it again, would it work? Yes. This would turn into this. So this is an example of having symmetry over the origin. So there's different tests you can use when all you have is an equation. We'll get to that in a second. But first, let's just look at this one simple example. If I were to plot the point -3, 2, and then they were to ask me to plot the point that would be symmetric to the x-axis from that point, I just need to think, what would that point become if I flipped it over the x? So it would be the point -3, -2. Now going back to the original point, this one, and now instead plotting the point that would be symmetric to the y-axis, it would just be, okay, what if I took that original point and this time flipped it over the y? Where would I be? Well, we would be at the point 3, 2. So that's just an example of using symmetry to just move a point if needed. If you're in my class, you'll see a question like that in the homework for this section. Okay, but now back to the test. If I wanted to test this equation for symmetry and I didn't know what it looks like, because obviously if we graphed it, we could just kind of look. But if I just wanted to use the equation, here are the tests. So if I want to know if it's symmetric over the y-axis, I'm going to replace all of the x's with -x. And then the way I'm going to decide if it does or does not work is if I kind of simplify that, can it look the same way it started, or is there no way? So this is what I mean. So I'm going to replace x with -x. That's step one. So wherever the x is, and if there's more than one x, I'm going to do this to every single one. I'm going to replace the x's with -x. Now, is there any way I could easily reduce this to turn into what it started with? No, there's no way. There's nothing I can really do. Those parentheses aren't even really needed. This does not match this, so it does not have symmetry with the y-axis. Now let's test if it's symmetric to the x-axis. So that test is, I'm going to replace the y's with -y, and again, see if it would become the same way it started. So here's how the graph started, or the equation. If I replace the y with a -y, it would look like that. And this time I can make this look a little nicer by actually doing the squaring, because squaring a negative anything turns it positive. So now do you see this looks exactly the way it started? So that means, yes, it does have symmetry in regards to the x-axis. Now, for both, I don't need to do anything again. I just need to look at what I just did. It definitely does not have symmetry over both because it worked for one and not the other. So far, it is only symmetric in regards to the x-axis. But now for the origin, I'm going to replace x with negative x and the y with negative y at the same time and see what would happen. So putting in negative y's there, putting in a negative x there, we can reduce a little bit, but there's no way to get rid of that negative that's in front of the x without messing everything else up. So no. So the only thing it has symmetry for, so it's symmetric over the x-axis is our answer. If you want to pause now and try the next one, so you can see if you're getting the hang of this, and then push play and see how I do it, that might be a good idea. So here I go. For the y-axis, again, we're replacing x with negative x and seeing if the equation could possibly still look the same way it started. In this case, again, we can do the squaring here, which would get rid of that negative. So, yep, that one works. For the x-axis, I'm going to replace y with negative y. So it's not too hard to remember that. It's kind of like when we do x and y intercepts. For x-intercepts, we plug in 0 for the y, and for y-intercepts, we plug in 0 for the x. So same thing here. To test symmetry with respect to the y, we plug in negative x. To test symmetry for the x-axis, we plug in negative y. So it's kind of along the same lines. Again, we can do the squaring here, which will again get rid of that negative. So this one worked also. So it has symmetry in regards to the y and the x. And now let's just test if the origin works also. So I'm going to plug in negative x for the x and negative y for the y at the same time and just make sure it would actually work out. Yep, this one will go away. Yes, that negative can also go away. So yes, it works for the y-axis, the x-axis, and the origin. Let me know if you have any other questions or have any problems that work out a little trickier than that, and I will try to help. Thank you.